Today I'm going to talk about the paper Climbing Towards Natural Languages Understanding on Meaning, Form, and Understanding in the Age of Data. Recently, there has been a hype in pre-trained neural language models. As larger and larger neural language models emerge, there have been increased claims that they capture various knowledge and meanings of the humans. In many of the press coverage, it seems like we are approaching the holy grail of artificial intelligence, or one of the holy grails of artificial intelligence, human analogous natural languages understanding. However, this paper argues that true human analogous natural languages understanding requires the structure and use of language and the ability to ground it in the world. Currently, the language modeling task, which refers to predict some strings, whether it operates on the characters, words, or sentences, the language modeling task operates only on the form of training data. And this article argues that this task cannot, in principle, lead to the learning of meaning. Further, the authors argue that the genuine progress in our field, climbing the right hill, depends on maintaining clarity around the big picture notions, such as meaning and understanding, in task design and reporting of experimental results. In section 2, this paper briefly reviews in ways which large language models are spoken about, and they summarize the current flowering of Bertology papers. In section 3, this article defines the meaning. Sections 4 and 5, this article presents some thought experiments to show that whether some components of the definition of the meaning leads to practical learning of language. And then in section 6, this article talks about human language acquisition. In section 7 and about distributional semantics, and section 8 about some suggestions for climbing on the right hills. And in section 9, they present some possible counter-arguments and the counter-arguments. Section 2 is probably very familiar to many of us. In, for example, the BERT paper, the authors says that in order to train the model, they understand sentence relationships. We pre-train the binarized max sentence prediction task. They use the term understand, and in several other works, they are saying that about comprehension, recall factual knowledge. On the other hand, the authors argue that quote several sentences that more adequately depicts the current state of the algorithms. For example, the systems are still a relatively long way from truly understanding their running pros. Though birds pass the lab's common sense test, machines are still a long way from artificial version of a human's common sense. In addition, in the Bertology phenomenon that happened a lot in recent papers, there has been significant flowering, like using the terms understand to depict their abilities. The authors argue that the use of these terminologies do not adequately depict their abilities. There are several examples that the neural language models rely on the forms instead of on the meanings to make predictions on classification tasks. For example, Niven and Koller paper. I happened to record a video of the Niven and Koller paper last week, And in that paper, it shows that when you change some sentences into this counter form of argument, the prediction task performance decreases drastically to uh, to almost trivial. This shows a lot about whether the neural language models like BERT rely on superficial forms when predicting. Now let's come to section 3. What is meaning? They first define two key terms. Form is about any observable realization of language. Meaning is about the relation between the form and something external to language. Meaning has communicative intent. The meaning of language is closely related to how people use them in the real world. The linguists distinguish communicative intent from conventional meaning. Conventional meaning of an expression is what stands constant across all its possible contexts of use. However, communicative intent can be used dependent on your context, the speaker, and the listener. This can vary a lot. In addition, meaning has significant grounding in factual knowledge. Turing argued that in order to say a machine can think, if a human judge cannot distinguish it from a human interlocutor or a computer. But the author argues that the criteria for saying that a machine can think should be much higher than that. We should be extra careful in devising evaluations for machine understanding. Then this paper refers to the South Chinese room experiment. In a room, there is a speaker who do not understand Chinese at all, but he has a dictionary that contain various rules so that it's able to give the correct response no matter what sentence this person is receiving. So looking from outside of the room, it appears as if the person inside the Chinese room understands Chinese, which the person inside do not. The person sitting inside the Chinese room is only relying on a dictionary that obviously captures only the form instead of the meaning. This thought experiment is about whether it's possible to manipulate forms well enough so that people think it's manipulating the semantics. But the authors argue that language is used for communication about the speaker's actual world. So the reasoning behind producing meaningful responses must connect the meanings of perceived input to the information about the world. This in turn means that for a human or machine to learn a language, they must solve the symbol grounding problem. Harnett points to the impossibility of a non-speaker of Chinese to learn the meanings of Chinese words from dictionary definitions alone. So as a recap for the meanings, in this section, the authors propose that when we say that something understands the meaning, we should make sure that the subject understands first the communicated intent, and second, the grounding in factual knowledge outside of the linguistic forms. Based on these definitions, the authors propose several thought experiments. This shows how absurd it is if we remove some critical components of the definition of meaning. The first is the octopus test. Let's say if A and B are communicating through a wire, and the wire is buried down the sea, and deep in the sea there is an octopus which can intercept the signals transmitting between A and B. And the octopus has a perfect dictionary, and it is able to generate responses based on what A sends, and except that the octopus is living its whole life deep down in the sea, so it knows nothing about what happens above the sea. So it doesn't know what is a bear, what is for example, tree. So when A is facing a bear and sending text message to B saying something like, please help, I'm in danger, but I have several chunks of wood. Please tell me how to assemble a weapon to conquer the bear. And this sentence is problematic for the octopus because the octopus does not know what is bear, does not know what is wood. So although there are some sentences in the octopus dictionary about these entries, it knows nothing about this about how to use them. The author actually gives several examples proposed by GPT-2 towards how they will answer this question. Robinson cried out, help, I'm being chased by a bear. All I have is these sticks, what should I do? The survivalist said, here's what you can do. Take one stick and punch the bear and then run faster to the store. Wait there until the bear is gone and give her all of the stick. Then go back inside and get your gun. The first sentence makes more sense, but later the sentence starts to be a little bit far-fetched. There are several other very interesting examples. It is clear that GPT-2 has learned uh, the activity words that tend to occur together with bears and sticks, like strap them to your chest, place the sticks, kill the bear, take your gun. But none of these complete actions will be helpful to A, because the GPT-2 does not. The authors argue that GPT-2 does not know the meaning of this prompt and the generated sentences, so they cannot ground them in reality. Okay, let's go back to the thought experiments. Another thought experiment is that if a language model learns is provided with all the codes in the GitHub, is it possible for it to learn how to write Java code? This thought experiment is very, very interesting and relevant because just a few days after, I think a few weeks after this article is published, a more powerful version of GPT-2 occurred with GPT-3, and there are some experiments showing that GPT-3 is able to generate some meaningful programs of like website or JavaScript by if you provide them with suitable prompts. But in this article, for the purpose of the arguments in this article, the authors argue that it's absurd to say that the language model learns Java because they do not know what it means to learn Java only by looking at the code. This is similar to learning English without communicative intent. So small children learn human language by attention and intersubjectivity. You need to let the children know both aspects so that they will be able to learn the language. By attention, I mean they should be aware of what another human is attending to. And by intersubjectivity, I mean they are able to guess what they are intending to communicate. Then in section 7, this paper talks about distributional semantics. Since several decades ago, distributional semantics has been the underlying principle of training neural language models, and this has been the prominent method for letting the NLP systems understand either the meanings or the forms. The distributional semantics proposes that the words with similar meanings or semantics tend to occur together in similar context. There are arguments that the learner gets access to more and more information in addition to the text itself. It can learn more and more facts about meaning. The authors acknowledge that this perspective is valid and meaningful, and this is an exciting avenue of research. Another point that this paper makes is that the slogan meaning is use refers to not the use as distribution in the text corpus, but rather that the language is used in the real world. In section 8, the authors talked about how to climb on the right hills. There are two paradigms of theory building, top-down and bottom-up, as the authors refer to. The bottom-up approach is that let's see which tasks that current systems can solve, and let's discover new tasks, and let's build better systems for this task. So we are making solid progresses from time to time. On the other hand, the top-down view tries to form a unified theory of this field, and later this unified theory might be falsified when we found new evidence. This is similar to what happens in physics when Newton proposes the three laws, and later this framework is modified by the relativity theory and then by the quantum theory, and new frameworks are proposed as new experimental results come out, and the frameworks evolve. The authors argue that instead of only looking at bottom-up view, a top-down view should also be looked at. In order to make some negative judgments that we were climbing the hill but not the right hill. This negative judgment can only be made from a top-down perspective. Followed by that, this paper proposes several best practices for mountaineering. First, above all, cultivate humility towards language and ask top-down questions. Neural methods are not the first bottom-up successes in NLP. They will probably not be the last. Second, be aware of the limitations of tasks. Third, value and support the work of carefully creating new tasks. Fourth, evaluate models of meaning across tasks. And finally, perform thorough analysis of both errors and successes. Then, this paper proposes some possible counter-arguments. Meaning doesn't mean what you say it means. Defining meaning is notoriously hard. For the purpose of this paper, they choose a working definition, which is as general as we could make it. But meaning could be learned from this and that. But there is so much form out there, surely that is enough. It is hard to say whether something is enough or not. But are neural representations meaning too? An interesting recent development is the emergence of models for unsupervised translation, trained only with language modeling objective or monolingual corpora for the two languages. If such models were to reach the accuracy of supervised translation models, this would seem contradict to our conclusion that meaning cannot be learned from the form. A perhaps surprising consequence of the argument would then be that accurate machine translation does not actually require a system to understand the meaning of the source or target language sentences. The bird improves the performance on meaning-related tasks, so it must have learned something about meaning. It has probably learned something about meaning in the same sense that syntax captures something about meaning and semantic similarity captures something about meaning. But we should really be specific about what is the something. As conclusion, this paper argues that, in contrast with some current hype, meaning cannot be learned from form alone.